Hello, and welcome to the presentation on extending TASTE inter-node communication capabilities by developing new communication devices using an MBSE approach. TASTE is a model-based software engineering toolchain developed under the guidance of European Space Agency and focused on space applications. It integrates various languages and technologies such as ASN1, C, C++, Ada, specification description language, message sequence charts, and Simulink. TASTE includes graphical editors, software libraries, and code generators, supports the definition of data models, logical and physical architectures, as well as behavior specifications. It also provides platform-specific threading and communication facilities, allowing to generate binaries targeting embedded systems. The toolchain supports platforms such as Linux on x86, FreeRTOS on ARM, and RTEMS on Leon 3, enabling design of heterogeneous distributed systems. The required inter-node communication within a distributed TASTE system is enabled by communication devices. A communication device is a kind of a device driver with a standard interface allowing configuration as well as sending and receiving of addressable messages. Its definition consists of ASN1 declarations of configuration data, ADL declarations for use by the code generators, XML declarations for use by the graphical user interface, and the actual C or Ada implementation. Though similar in the idea, TASTE communication device can be a bit different from a typical embedded device driver, as in order to achieve its desired function it may orchestrate more than one hardware peripheral if coordination is required, or command no hardware at all, as in the case of a purely software-defined channel. It may implement a higher-level communication protocol, for example to manage traffic on a physical link. It can also provide message encapsulation and extraction from a data stream if the channel does not provide a native support for data frames. The communication devices provided with the TASTE toolchain are manually coded. It is the simplest way from the toolchain point of view, as it does not require any additional tooling. It is also the most flexible and efficient way, as there are almost no design constraints or abstraction overhead. Of course, given the design flexibility, the efficiency and maintainability of implementation is entirely up to the user. However, this approach is complex for new users as it requires in-depth knowledge about TASTE internals. It also does not offer the benefits of a model-based approach, such as, for example, convenient integration of various technologies and use of high-level constructs which are easier to document, trace, analyze, and verify. Of course, taking advantage of these possibilities via proper design and usage of other tools is entirely up to the user. ISA contract validating sets as a bridge between hardware and software models, executed within the scope of OSIP model-based system engineering campaign study scheme, introduces the capability to design TASTE communication devices using a model-based approach. Space Creator integrated development environment provides a new project type, reusing familiar editors for interface view and ASN1. Data model for devices context and interfaces is defined using ASN1 and ACN. Logical architecture is defined explicitly via interface view. Implementation can be provided using both traditional programming languages such as C, C++, or Ada, and modeling languages such as SDL and sets. Of course, different functional blocks can be implemented using different technologies, allowing to use the best tool for the given task. A communication device project can be built for distribution and installation, in which case SDL and sets models, if present, are translated to Ada or C using TASTE code generators, and the necessary glue code and declarations for use in the toolchain are automatically generated. Let's showcase the tooling on some examples, starting with a basic one which aims to present the developed tooling and the communication device design process. In order to simplify the demonstration, a simple TCP/IP-based device is created for a Linux system reusing an existing implementation, details of which are considered unimportant and therefore not shown. A more complex use case showcasing the MBSE approach and its potential benefits will be presented in a later example. The following items are discussed: project creation, the artifacts generated by the project wizard, ASN1 configuration, and finally, project build and usage. Space Creator now supports a new project type, a communication device project. Let's create a simple TCP/IP communication device sending and receiving data via a Linux TCP/IP socket. Two variants of the communication device project are available. A base communication device project, which exposes only the runtime broker interfaces required for sending and receiving already packetized messages, and an extended project, which additionally exposes packetizer interfaces, allowing to define custom, device-specific message encapsulation. The topic of packetization will be addressed in a later example. The templates are target platform specific. Currently, only Linux on x86 and FreeRTOS on ARM are supported. However, porting of the templates to another platform already supported by broker-based runtimes is quite simple. Finally, we need to specify the class of the supported bus. This is required for Space Creator and Ocarina to validate that endpoints connected in the deployment view are compatible. In our case, we use a standard TCP/IP bus. Now let's take a look at the generated artifacts. Ocarina Components contains ADL definitions required by Kazoo and Ocarina for code generation. The contents of this file will be integrated with the master taste Ocarina Components file during the device installation. Users should not edit this file manually. Pod 1 contains XML declarations required by Space Creator to expose the device to the user in the deployment view. Users should not edit this file manually, except for changing the port name. The contents of this file will be integrated with the master boards file during the device installation. The generated interface view contains a single broker adapter exposing the necessary interfaces. This entity is marked as immutable, enforcing proper interface signatures. Let's add a pre-made implementation. The chosen implementation language is C. The init interface, called upon system start to initiate the device, is synchronous and protected, containing only the initialization data as its parameter. The initialization data includes configuration of both the local device and the remote device connected at the other end of the bus. The deliver interface, called each time a message is sent, is asynchronous sporadic and contains a single parameter which includes the message to be sent. The receive interface, called each time a message is received, is also asynchronous sporadic and contains a single parameter which includes the received message. Now let's take a look at the generated ASN1 models. The driver ASN1 contains base type declarations used in the adapter interfaces, and so it should not be changed by the users. The private data ASN1 contains the data model of the internal device context, pointer to which is passed across interface invocations. As our pre-made implementation is already written in C++ and has its context defined in a C++ class, let's define a simple byte buffer to hold it. The device configuration ASN1 contains the data model of the configuration, which will be exposed to the user in the deployment view and passed to the device via the init interface. Let's paste a predefined configuration of an TCP/IP endpoint. Let's edit the user function. We will use a pre-made implementation written in C++. Let's copy it to the source folder of our function. Now we'll paste a pre-made adapter code which bridges the interfaces between the pre-made implementation and our function. The receive interface is called from within the pre-made implementation. Now let's build the device project by clicking the build button. Please note that this button should be clicked when the interface view is active. The project is built. The build folder contains the sources of the generated glue code, including threading facilities, adapters, and the communication device interface that was described in the Ocarina Components file. Now let's install the device and use it in a demonstration project. Installation copies the source ASN1 and code files and integrates the board 1 and Ocarina Components files with the respective masters. The demonstration project consists of two functions, one periodically sending a ping and the other responding with a pong. For simplicity, both are implemented in C. The tick cyclic interface is responsible for the periodic activation. Ping sporadic interface carries a single integer parameter. and the Pong sporadic interface also carries a single integer parameter. Let's copy the pre-made implementations. Now let's create a deployment view to use the previously created communication device. We deploy our logical architecture to two nodes, each representing a Linux application. The nodes expose sets of ports among which we can find our demo TCP/IP device. Let's connect the ports and set the required configuration. Let's bind the functions to the nodes. And finally, let's bind the interface connections to the bus. Now we can build the project. Let's start partition 2, hosting the function responding with a Pong. And partition 1, sending the ping and receiving a Pong. The messages sent via a communication device contain logical payload and addressing information, as well as other data, such as protocol metadata or checksums. Encoding on the messages to a transmitted data stream is referred to as packetization. The same way, decoding of the messages from a transmitted data stream is referred to as depacketization. Different use cases have different requirements on their transmitted packets. For example, checksums may be required on some physical links which can be unreliable, especially in a challenging EME environment. However, for logical links, such as TCP/IP, additional checksums may be redundant. Protocol compliance may be required for interoperability. For example, PuSC standard requires its requests and responses to be encapsulated in CCSDS space packets. TACE provides a set of built-in packetizers, which are selectable in the deployment view. However, a communication device may introduce its own custom packetization scheme, if required. The following example presents a project containing a communication device with a simple custom packetizer. The following items are discussed: packetizer interfaces, and the additional artifacts generated during the project build process. The project has been created using the broker and packetizer template. The broker adapter function exposes exactly the same interfaces. The packetizer adapter function exposes three new synchronous protected interfaces: init, packetize, and depacketize. Init interface contains only a single output parameter, header size, which is used internally by the broker to correctly offset the user data, thus allowing to build the packets in place without unnecessary copies. The packetize interface contains the following input parameters: packet type to indicate whether a telecommand or telemetry is expected, pointer to the packet data buffer, and the packet buffer size. On output, it produces the extracted packet source and destination, offset to user data size, and finally, the error code indicating whether the decoding succeeded or not. Packetize interface contains the following parameters: packet type indicating whether telecommand or telemetry is to be encoded, source address, destination address, pointer to the packet data buffer, offset to the user data, and finally, length of the user data. Now let's take a look at the implementation. Here we can see an adaptation of a minimal packetizer which performs rudimentary sanity checks and encodes only the data size and its destination in its header. And now let's build the project. There is an additional artifact, an automatically generated packetizer adapter, which adapts the ASN1 base interface view parameters to native C1 supported by the runtime broker. Let's proceed to the final, more complex example which aims to present the following capabilities: implementation of a simple communication protocol, orchestration of more than one hardware peripheral, and integration of different implementation technologies. For this purpose, a pair of RS485 drivers is introduced. Linux one, acting as a coordinator, internally using a Linux driver for the RS485 dongle, and some v71 one, acting as a subordinate, using UART for data transmission and parallel input-output pins for the management of an attached UART to RS485 bridge. The following items are discussed: driver architecture, sets usage, project build and usage. RS485 standard supports multipoint communication over linear bus topologies, enabling creation of inexpensive local networks, used for example in industrial applications. This is achieved using only two wires thanks to three-state logic. When one transmitter is enabled, others are disabled. However, the standard itself does not define a protocol, only the electrical interface. Therefore, we provide our own. The following implementation is presented. The dongle attached to the Linux system manages the transmitter automatically. UART to RS485 bridge exposes a pin to manually manage the transmitter. Coordinator transmits when it's not busy receiving. Coordinator periodically sends a token, switching to the receiving mode for a given time window. And finally, subordinate transmits only within the time window after receiving the token. The RS485 communication device consists of an arbiter, responsible for handling the described protocol, acting as a subordinate, an assembler, responsible for disassembling and reassembling message into and from individual bytes, which are escaped to accommodate frame start and stop markers, UART, responsible for sending and receiving the individual bytes via the hardware UART peripheral, PIO, responsible for managing the IO pin controlling the UART to RS485 bridge direction, and FAS, responsible for exposing the SAMv71 memory address space in interrupts to the UART and PIO functions, which are defined using a high-level language and cannot access the low-level hardware resources directly. Of course, the user-defined logic is connected to the broker adapter. To speed up the presentation, the interface view functions are already imported and their interfaces are connected. Let's take a look at the function implementing the low-level UART driver. Its behavior is implemented using sets, a CCSDS XML-based format used for describing data types, interfaces, and state machines. A dialect of sets is natively supported in taste, illustrating the technology integration capabilities. The assembler function interfaces with the UART driver, is written in C, and uses a separate library for handling the message escaping. The arbiter function, also written in C, is interfaced both to the assembler for message transfer and PIO driver for managing the transceiver. The implementation is quite short, clearly illustrating the separation of concerns. Now let's build the project. As you can see, the sets-based implementation of the UART driver was translated into ADA, which will be included in the installed communication device sources. Let's perform the installation. In order to communicate with the SAMv71 node, a separate RS485 driver must be provided for Linux. It is much simpler as it includes only the arbiter, responsible for protocol handling, acting as a coordinator, and the dongle driver, which is a wrapper on the driver available in the Linux system. For demonstration, let's reuse the system created for the first example. In order to deploy it to a different hardware target, we just need to create a separate deployment view. Function 1, sending the ping, is still deployed to a Linux partition, while function F2, responding with a pong, is deployed onto a SAMv71 partition, which is an application binary deployable to the embedded target. Let's configure the system. And now, let's build both partitions. First, let's launch the SAM-v71 partition. The SAM-v71 explained Ultra board is connected to a Raspberry Pi, exposing the debug interface to the network via OpenOCD. Let's connect to it, upload the partition, and start its execution from the reset handler. The hardware dongle interface is forwarded from the hosting Raspberry Pi to the taste virtual machine via socket. Now let's launch the Linux partition. The communication works. The logs show both the send and receive data, as well as sending and receiving window information. Let's summarize the presentation. Communication devices are required to provide communication between nodes of a distributed system via various channels, ranging from UART or RS-485 to TCP/IP sockets. A new Space Creator project type is introduced specifically to design communication devices. The necessary glue code and taste declarations are generated automatically, greatly simplifying the communication device implementation process. The communication devices can be designed using an MBSE approach, which facilitates the integration of various technologies, such as for example SDL with C, allows the use of high-level modeling languages, such as SDL, with the corresponding benefits and trade-offs, and finally, it also makes it easier to implement higher-level protocols. This concludes the presentation. Thank you for your attention.